This is a paper that I presented at the ATM seminar a couple of years back, done with some of the colleagues from elsewhere in the world. Essentially, here we are looking at the difference between drone operations or small unmanned aerial systems versus urban air mobility. So we've been talking a lot about the difference between UTM/UAM and conventional aviation. Here it is drones versus UAM, well, and also the conventional aviation, so finer grade look. So it's probably not surprising that a lot of markets, at least for UAM, are within the congested airspace with a lot of ground obstructions, with these sensitive areas, sensitive from the point of view of security and so on. And of course, there are procedures, the aircraft procedures, as we saw in Stockholm, that in the cities have some influence on where UAM can fly. So understanding what the available airspace is for urban air mobility is critical for many reasons. In particular, in many places, so here I'm showing the Bay Area near San Francisco, and yeah, the examples I will show here are more from there, somehow spawned by the American colleagues. So a lot of surface level airspace is already controlled by air traffic services because it's close to the airport. And also, so here are the procedures from the conventional aviation, similar to the graphs that I showed you for Stockholm. And the conventional aviation, the legacy users may take priority over UAM because we don't want to move them just because of UAM. And looking at the big picture, what we want to do for UAM, well, we want to understand what airspace is available for it. So, you know, you don't want to fly through the buildings. So these blue represents kind of, I just drew some schematic representation of where the UAM vehicles can fly. And then you have to look on the ground and understand what are the feasible areas from which the UAM vehicles can take off and land. And again, here is the picture from Norrköping, but in general, you have to understand where they are. And knowing what the available airspace is and what are the ground areas, you have to do the network for UAM, how they will fly between the different takeoff and landing areas. Moreover, you have to do some kind of sensitivity analysis and understand how this is influenced by runway configurations, by aircraft performance. Is it strict vertical takeoff and landing, or do they go on an angle? How it depends on weather, and how it depends on integration with ATC, with air traffic control. And what I will speak about is this part, looking at different integration with the air traffic management and different concept of operations for that, how the available airspace changes. So there have been other studies that look at that, but most of them are kind of conceptual. So they draw pictures of how the airspace may look like, but I don't think any city really looks like this. So there are not these cuboid volumes. This could be something that, you know, I would call spherical city in vacuum, referring to this joke about a scientist to whom a farmer comes and says, well, I know I need to have some help with my cows. And the scientist goes on and produces some results, and then they are not applicable in reality. And the farmer is complaining to the scientist, but the scientist says, well, what can you do? All my models are for the spherical cow in vacuum. So here, these cities are somewhat far from reality. So could call them spherical cities in vacuum. And it's interesting how the real available airspace looks like. So there has been quite a few thinking also from Uber Elevate, who are trying to start UAM services. There were partial considerations looking at the ground obstructions at the airports, and also at the flight operations, but there was really no integrated study to understand how the various components of the airspace influence airspace availability. So essentially what is needed is to identify what are the obstructions, what are these airspace constructs that are used by air traffic control, develop the 3D models of these constructs, understand how we are integrating UAM with ATC, and identify the airspace which is not contained in any inaccessible airspace. So in other words, identify the available airspace. And last but not least, evaluate some KPIs on the available airspace, how good the UAM routes will be. And I will show some examples again on the Bay area, but it could be also done for other areas as well. So what should be excluded from UAM operations? Well, it depends on how you integrate with air traffic services. So there are some temporary flight restrictions. There are airspace that requires active air traffic control or passive air traffic control. There is also airspace like Class G airspace where you don't have interaction with ATC at all. So come to think of it, you can define, I guess, at least 8 types of obstacles that should be avoided by UAM flights. And of course, you don't want to fly into the buildings. You may want to avoid special flight rules area. You may want to allow airport procedures, and either all procedures are only active, temporary flight restrictions. There is something called minimum vectoring altitudes above which the air traffic control may still vector the conventional aircraft off the published routes. Then there is lower part of the airspace for drones, which may or may not be used by a UAM. And yeah, in general, the whole controlled airspace for the for an airport may be a no-go zone for the drones, for the UAM, and for the drones too. As we know, there are some of these incidents when the drones got into controlled airspace and then the whole airspace had to be closed. And I'll show the pictures of these constraints. So here are the terrain and or the buildings, and there are certain vertical and horizontal offsets that are added to the buildings. The UAM vehicles have to stay clear of the buildings up to certain length or the horizontal or vertical distance. Then there is a special flight rule areas. I don't think they exist much in Europe, but basically you can go with VFR traffic even through active procedures and even above the runways. I guess that's not very relevant for European context. Airport arrival and departure procedures, relevant everywhere. In no place in the world you want to hit a departing or arriving aircraft. Now, there are 2 different ways at which you can look at the procedures. You can only look at active procedures which are in use now, or you can say whatever can be ever used by the aircraft around the airport should be an obstacle for UAM. So these are 2 types of the constraint. Special user space, of course, there are some security restrictions. You don't want to fly there in general. Minimum vectoring altitudes, again, if the aircraft may go off the procedures due to vector instructions from the controllers, maybe you don't want to fly there with your UAM unless UAM has interaction with controllers too. Right, so the drone airspace for small drones, well, maybe you allow UAM in, maybe you don't. And last but not least, yes, the controlled airspace around the airports. Do you allow the UAM traffic there? Do you not? Well, that depends on the concept of operation. Okay, so I described 8 types of possible constructs or possible obstacles for the UAM vehicles. In general, if you have K types of these constructs, you can take any subset of them as the obstacles, and well, you can have 2 to the power K subsets of K types of objects, K types of constructs in this case, and have lots and lots of interaction scenarios. But of course, you're only interested in them if they exist in your region of interest and the air traffic control limits the access to it. And even from our 8 constructs, you could create 256 due to the 8 different integration scenarios, but instead we picked just 4 integration canopses, and I will go through them one by one and show some pictures of how the interaction between the conventional air traffic control and UAM may look like. So the first one is, let's say you don't want to contact air traffic control at all. So you essentially fly here in this green zone, in this very low level airspace. Of course, not going into the buildings, but more or less you are bounded by not by the height, different height at different places. So you don't want to hit the buildings, and you are not allowed into the controlled airspace a lot. So there is no workload for controllers. They don't see UAM, no regulatory changes, simple, but who knows how much airspace is available in this case. Another possible integration ConOps is that, okay, you do not fly in the drone's airspace, and you do not fly in the neither in active or inactive airport procedures, and do not fly where the controllers may vector the air traffic. So essentially, this is the full separation. So the small drones stay here underneath, the aircraft stay here, and the green area is where UAM may fly under this integration. Well, this is actually a low level of integration. This is fully segregated, but again, if you look at the integration scale from fully segregated to fully integrated, well, that was fully segregated. Now you can be integrated, but what we call statically integrated. So you can fly where the drones fly, close to the ground, of course, not hitting the buildings. And you can fly anywhere in the controlled airspace, but not where the aircraft, the conventional aircraft can fly, not in the airport procedures. And last but not the least, the kind of full integration, which may be somewhat visionary, maybe can be called UTM 2.0, and sometimes this future UTM is called Unified Traffic Management. So U stands not for unmanned, but unified, where you have such a good integration with the air traffic services that you know that certain procedures are inactive, and hence you can fly here. You can fly everywhere except for the places where the aircraft are actually flying, and you know well where it is because of the good integration. So these are the four concepts of integrations. For each of them, we have some airspace constructs or obstacles, not going into details how we do the processing. Get into some of the pictures of how the results may look like. So we choose some kind of region of interest to encompass some points of interest in the Bay Area around San Francisco. And here is how the available airspace looks like. So in all these pictures here on the right, for the different integration ConOpses in different columns, white is the available airspace. The rest are the obstructions, the obstacles, colored differently according to what they are. So this black color are the terrain and buildings, and they're of course only relevant at low altitudes. And then the controlled airspace goes, it's the wedding cake, overturned wedding cake. You see how this pink, how the controlled airspace increases in area as it goes higher and higher. So again, not going into all these pictures in details, let me show you what can be said as a CAT scan of the airspace, so short YouTube video. As you go in higher and higher in height, there are different parts of airspace that become available or unavailable rather under the different integration scenarios. Okay, so now that we know where you can fly, what is your available airspace, you have to understand how good it is. Just looking at it is one thing, but you also want to be quantitative and compute some of the KPIs. And well, there are 5 KPIs that you may look at. Well, just the percentage of the region of interest that's available for UAM, percentage of accessible population, that's interesting from the business point of view, how connected your airspace, convexity, I will show what it is, and this route stretch, how much you have to stretch your route because of the constraints. And again, not giving you all the details. Let me show you the pictures. So here you have green is excluded area, and everything which is not green is where you can fly with the UAM. Well, then you have certain regions where you can fly, and there's certain percentage of airspace available and certain percentage of population. And you can look at this under different concepts and also different heights. So here is how the percentage depends on the height, on the altitude. And you can see that, well, maybe around a couple of 100 meters, 200 to 300 meters is where the airspace most available for the flights. So maybe actually for different concept of operations, different integration canopsis, it's pretty consistent. This is where you want to fly. So maybe this is the good height for the UAM to fly. So you're already above the terrain, but below all these constructs that come from the conventional air traffic. Now this is the path stretch. We will look more into the road stretch factor in another lecture on applications. But here again, you may look at this ratio. If you could fly anywhere you want, you could go by a direct path, but instead you have to go around, and the ratio can give you, some kind of indication of how good or bad your airspace is. And yes, for some points of interest, you can see how the routes go around the forbidden areas, which are here in pink, and you can see the route stretches for the different routes. Again, I'll show you this. I'll refer to this picture again when we study the shortest paths. And yeah, you can do this comparison under the different metrics and in different heights. Okay, so to conclude, yes, understanding what airspace is available is important, and you have to look at different kinds of constructs. You may see where the good places for the vertiports are, depending on the performance of the vehicles. And here again, I'm referring to the recent EASA video, which shows these flight envelopes they envision for the UAM flights. Yes, you can see what kind of required navigation performance you should get from the conventional aircraft and how that influences the airspace. So RNP1 is essentially the aircraft should stay within 1 nautical mile of the center line, and with much better RNP, advanced RNP, you can have the aircraft follow the center line with higher precision, and then you see how much more airspace becomes available for UAM. Then yes, there are different ways in which you can try to understand what is the airspace occupied by the conventional aircraft. You can look at historical data or look at the published procedures, SIDS and STAR, standard instrument departures and standard arrival routes. You can do airspace assessment as well suggested by Eurocontrol. I hope it will be mandated sooner or later. You have to look at ground risk, and that's something we've done in the previous lecture. But you also should look at air risk, obviously. And here is how you can use our approach to do the air risk, understanding of air risk. For the airspace availability, any piece of airspace, if it's available, we assume that there is low risk. But of course, depending on whether you have the risk of hitting an aircraft, that depends on how good the containment of the aircraft trajectories are, how closely they follow the center line. If you look at the vectoring here, the aircraft is vectored, then again, it depends at how often it happens and what the controllers say at that time. If this is something known in advance, then UAM can avoid such errors. But if the controller really is trying to get an aircraft out of collision, then the controller also has to deal with the UAM, that's probably not good. Anyway, so different types of constructs they lead to different kind of risk, and you can understand that. So there is more work that has been done on similar topics. I don't want to go into details of that. And one remark is that it's very important what the boundaries of the UAM airspace are. So here, some of the routes would have to be very long if you have to stay within these boundaries. But if you have larger boundaries, then the routes are smaller. And that's, again, the big question of what kind of airspace is UAM airspace, whether there will be U space or UAM space or something else. That's more or less an open question. Visualization, yes, we have to visualize these available airspaces. And yeah, again, there is some work done by Uber Elevate. And last but not least, you have to present the available airspace in some kind of human graspable way, and not as we have with this CAT scan that I'm showing here on the right. Okay, so yes, just one slide with the big picture. You're understanding what airspace is available, from where to where you can fly, and eventually, hopefully, design the network for UAM, taking into account all possible constraints, different kinds of integrations with ATC, but also other things. Okay,